Today, I'm here with David Chanin, a fourth-year PhD student in the Foundational AI CDT at UCL. We're going to talk about his research on sparse autoencoders and his experience on the prestigious AI safety research program, MATS. Welcome, David.
Thank you.
So your research has been on sparse autoencoders, but before we get to that, let's start with the problem they're trying to solve. So can you describe for us what mechanistic interpretability is and why it matters what's going on inside neural networks like large language models?
Yeah. So it's like mechanistic interpretability. You're trying to answer this question of what's going on in this giant black box that are these language models. 'Cause they're doing all this incredible stuff, and it's kind of, well, I mean, it's both very impressive and also kind of terrifying that we don't really understand concretely what they're doing internally. Especially as we're, turning more and more things in the world over to AI, and we don't understand their failure modes. Like, you know, uh, it's kind of like we were writing all this software, but we don't really have a debugger for it. We don't really understand like what the code's doing. We're just running it and being like, yeah, it seems to work. Like, I don't know, what could go wrong? Uh, and so yeah, so interpretability, you're trying to, I guess, try to make this less of a black box via whatever method possible. Um, and I don't know, I think this is important for a couple of reasons. So one is just like scientifically, it's very interesting that we have this kind of alien brain that we can study and try to understand. It's like doing all this incredible stuff. And I think we'll learn a lot about just the nature of intelligence and learning and things like this if we can understand how these models are doing it. But yeah, I mean, there's also kind of like the safety angle of like it's actually kind of scary to just have these things we don't understand that are doing incredible stuff, and then we're turning more and more, control over the world or the economy or whatever over to. Um, yeah, because I guess like you can think of these models as, I mean, it's almost like raising a child, I guess, where it's like, you can kind of give the child feedback, but you don't really understand what the human brain is doing internally concretely. And it's kind of like this with these models too, where you can just give it examples of things you want it to do, and it seems to get better, and you kind of can scold it when it does poorly, and it seems to sort of take these lessons, but you don't really, I don't know. Yeah, it doesn't instill a lot of confidence in the same way that, if you're building like an airplane, like you really do understand everything that's going on internally and like all the forces involved. And if something goes wrong, you can debug exactly what it was and fix
Mm.
the issue.
Yeah, I think that's a really great analogy
Oh yeah, yeah.
because
Thank you.
because sometimes when I talk to people, I say like, okay, we don't understand these AIs we've built, and they're like, okay, how can you not understand it when you built it? How does that work? But yeah, it's not like an airplane where you understand every component and how it fits together and the purpose of each thing. Instead, it's just like billions or even trillions of numbers in a computer that we tune over and over again until it does what we want it to do, without knowing what each particular dial, what its function is in the entire network. I mean, we know what its function is on like a low mathematical level, like it increases this number, which increases the weight for that neuron, etc. But you can't understand it just on this level of here's a billion numbers and they have these values and they interact in this way. It'd be like trying to understand a human brain based on like all the synaptic connections and the synaptic weights. You still wouldn't be able to like understand why they did what they did.
Yeah, yeah. I think it's a good analogy as well. Yeah. I mean, I guess we probably do understand for like the human brain, like what an individual neuron does, and yet we still have no idea how these combine into the human experience and all this stuff. So it's, um,
Yeah. I think even an individual neuron, we're not quite confident we
oh, are we done?
understand,
Yeah, I
but
probably shouldn't even say that. Yeah, I actually have no idea anything about neuroscience. Yeah, it does give me a lot of newfound respect for neuroscientists because it's like, if it's this hard, even when you have full access to every neuron that's firing, you can like stop it and intervene on it and like run it forward and
Mm,
backward and all this stuff you can do in these like like virtual neural networks. It's like for actual neuroscience where you have like a human brain or animal brain or something like, and you can't do any of that. It's like, how they do anything? Like, this is really hard, even if you do have like full access to everything that's happening.
yeah. You're like with a neural network, you can pause it halfway, run it again, and you'll get exactly the same result. But with wet, squishy brains, it just doesn't work like that. There's no rewind
Yeah,
button,
exactly,
and it's not
exactly.
repeatable.
Yeah,
So interpretability is this idea of like trying to figure out what's going on inside the neural network. But what's this idea of mechanistic interpretability specifically?
Yeah, I think there's like a lot of, I don't know, debate over what this term actually means or if it means anything. It's like a bit unclear if mechanistic interpretability is concretely different than just interpretability. I think initially it
Mm,
started off with this ambitious goal of like, we're going to reverse engineer the entire neural network and we're going to understand everything that's going on to the point that we could like write Python code that would reproduce it. And um,
mhm.
it seems like that goal, people are no longer as bullish on this goal, um, which to me is a little bit sad. I think it would be good if, I don't know, I guess there's, well, I mean, I think a lot of this is kind of mixed up into this idea of like AI timelines and how long do you think, until we get some kind of super intelligence or something. But because I feel like with most fields of science, like for instance, in biology, if you're like, oh, we didn't solve biology fully in like 2 years, I guess it's worthless and we should give up. It's like no, that's like crazy. Like like it takes more than 2 years to understand all of biology. Like I think we're kind of a similar thing here where it's like people got very excited and were like, could reverse engineer some kind of simple neural networks and made some exciting initial progress. And then everyone's like, cool, we're just going to do this for everything, for full neural networks, to understand everything about them perfectly. And we're going to do it instantly. And it's like, okay, well, that didn't work out in a few years. So I think people are like, well, at least for the safety case from interpretability, it's like we kind of need to make a lot of progress in this very fast if we're going to, it's going to be worth it. And maybe like understanding everything 100% completely is a bit too ambitious. So yeah, I think the term mechanistic interpretability, I don't know. I don't actually know if it really means anything concretely at this point because I don't think most people who say that they practice mechanistic interpretability are actually trying to reverse engineer everything in the neural
Mm,
network still. Um,
mhm.
I think it's kind of like become this generic term for just like we want to understand what the neural network's doing internally, some kind of like white box access to what's going on internally. And it's like, I mean, I guess maybe it's similar to biology as well. It's like you have people looking at like individual cells. You also have people looking at like, organs and kind of like, kind of these like, it's not like you have to go down to the level of like molecules to say you're doing biology or something. It's like, no, it's all useful. We can look at any level. It's still going to be
Yeah,
useful stuff there. I think maybe
yeah.
mechanistic interpretability has kind of become like this where you're like, but yeah, I don't know. I kind of wish the term didn't exist because I think it's just confusing at this point.
So I gotta ask a question I know is stupid, but I want to see your response to it, which is, why do we need to do any kind of interpretability on LLMs, given that they just tell us what they're doing?
Yeah, I mean, I guess it's like, how do you know that they're telling you what you're like actually faithfully? I mean, I don't know. I mean, I guess in the same way that it's like you could say the same thing about like the human brain. You're like, oh, who cares about under neuroscience? We'll just ask people what they're thinking and they'll just tell us. It's like, no, we still actually want to know like scientifically what's going on, and there's like a lot of insights to be gained. And I honestly don't think these
Hmm.
neural networks even know a lot of the times why they're doing what they're doing. In the same way that like you don't necessarily know like when some thought pops into your head, it's like why exactly did that pop into your head? It's like I don't know, or
Yeah,
like um yeah, there's a lot of these like kind of failure modes and biases, and I don't know, just like weird things that models do that you can't really get at just from asking them. And a lot of times, if you do ask them, they'll come up with some like post hoc rationalization that's like clearly false or like very obviously not true, but it sounds convincing, and I don't know.
yeah. My favorite example of this is that Claude like doesn't seem to understand how it adds numbers. Like they did manage to reverse engineer how it adds numbers, and the true method it uses is different from the method it says it's using. So you just can't trust what they're saying.
Yeah, yeah, yeah. That's very true. Yeah, I mean, I think it's like, um, but I think it's the same for like humans too. Like if you just add two numbers in your head, like your brain just like comes up with the answer, and it's like, well, but how? Like, tell me how exactly your brain did that. It's like I don't know. It just come on, man. Just you just do it. Like I don't know.
So I wanted to get your take on this quote from, so there was some evidence given to Parliament, submitted to Parliament in 2024 by Andreessen Horowitz, who runs A16Z. And I think it might shock you because it actually says that your work is a waste of time because it's all been solved already back in 2024. So, so He wrote to Parliament, although advocates of AI safety guidelines often allude to the black box nature of AI models, where the logic behind their conclusions is not transparent, recent advancements, this was in 2024, in the AI sector have resolved this issue, thereby ensuring the integrity of open source code models. So what are you doing, David? I don't get it.
Yeah, I should ask Mark Andreessen what maybe he has all the answers, just isn't publishing them or something. Uh, I guess like for Mark Andreessen specifically, he has a very strong vested interest in like not being regulated because he wants to make lots of money on AI and like things like, oh, what about safety issues get in the way of that? Then that would be less money for him probably in the short term. Although I don't even think it makes sense for him to downplay this stuff if there is an actual AI problem, like serious AI, incident, like safety incident. I think it's going to be bad for his investments too. But uh, yeah, I mean, so there was a brief period, I guess, in 2024 when sparse autoencoders kind of first were showing a lot of promise for interpretability, where you know, like I mean, Anthropic was kind of hyping this up, and then there was people who were like, "Oh wow, I guess we solved it. I guess sparse autoencoders just solve everything, and we'll just go around high fiving each other." And then I guess Mark Andreessen was like, "Cool, now I don't have to care about safety. Let me just tell the world to shut up about safety. I'm gonna go to the UK Parliament and tell them everything's solved." Uh, and yeah, that's maybe it was a bit premature. Um, so yeah, I don't know. I guess like I work at Sparse Autoencoders. I don't. Well, yeah, there's a lot of issues with them that need to be resolved. I hope that they can be resolved, but at least at the current stage, they are definitely not a silver bullet. And Mark Andreessen, uh, yeah, maybe should have calmed down a lot. Um, but I don't know. I
That's
suspect he knew what he was doing. I suspect that this was not like like he totally didn't know that we haven't fully solved all safety problems. He's just like kind of probably just wants to the UK Parliament to chill out and let him make money and not tell him to like worry about any potential harms.
yeah. I mean, to be fair to him, that he wasn't the only one overreacting on Twitter, but it's def. I don't believe for a second that he believed that AIs were no longer black boxes.
Yeah, it seems like that'd be a pretty shocking thing to suddenly believe, but who knows? Who knows? He's a strange guy.
All right, so let's dig into sparse autoencoders. So the field of mechanistic interpretability has like its own kind of language, a little bit of concept or feature, superposition, etc. So I want to go through a few of those. So maybe let's start with concept or feature. So my rough understanding is that mechinterp is trying to you've got like the high level behavior of the model, like the text it's outputting, and then you got the very low level behavior of the model, which is like which neurons are firing with which activations, etc. And concepts, it's like you're trying to construct something somewhere in the middle that like is human understandable and explains the behavior of the model.
Yeah, a concept could be like anything, I guess. It'd be like this is a dog, or like this person is named Ruben, or like I don't know. Yeah, just like anything that any kind of representation of knowledge or state or something inside the network. I mean, it is like a very fuzzy term. Um,
Mm.
and like yeah, so I guess there's kind of like a few levels. There's this level of circuits, as it's called, where it's you can imagine if this is a computer program, there's like kind of the logic of the program, and that's kind of like the circuit. And then there is the actual variables that are at any point in the program. That's kind of like the features or the concepts. It's like so. I guess you'd hope that sparse autoencoders or something like this would be able to tell you like it'd be kind of like a debugger and code where you like hit a breakpoint and you're like, okay, what are all the variables in memory? Like what are their values? Um,
Mm.
and then it's like, that's not the full picture. Like you still want to know like what's the program doing with those variables, but that's still going to give you a lot of insight if you can even just see what the variables are at any point in time. And then hopefully once no, and also like knowing what the variables are should also help you figure out what the logic is too, because you can kind of watch the variables mutate and stuff.
So when an LLM is predicting the next word, it has these activations that flow through the network. And some of these activations are like vectors, right? They point in a particular direction. And we want to say, okay, when the vector is pointing in this direction, that means the LLM is thinking about or it's representing the concept of dog or some grammatical concept like a parenthetical, etc.
Yeah,
So our job is to try and like break down these activation vectors into concept vectors.
yeah, I think that's basically right. So initially, people thought, um, well, maybe if we just watch an individual neuron in the network, we can figure out what that neuron's doing, and each neuron's going to be doing something that's very like understandable. And if we just watch it, we can just kind of figure out what it's doing. So you kind of see like you have like neuron 137 or something in some layer of the model, and you're like, all right, like when does this thing fire? And you could see like, oh, it fires on like Spider-Man. Like anytime Spider-Man's mentioned, like this neuron will fire, and you're like, oh, great, this is like the Spider-Man neuron. Um,
Hmm.
and but then it's like, people kept finding that like it's really hard to actually find neurons that only fire on one thing. Like, so if you keep watching, you might think it's Spider-Man, but then you keep watching it more and you're like, oh crap, like actually it seems to sometimes fire on like French poetry. So it's like kind of hard to say like this neuron is okay, it's Spider-Man, but also sometimes French poetry. And then you're like, oh, but sometimes it's like the number 17 too. I don't know. It's like you get kind of these like weird mixes of things, and it's kind of hard to even say what's going on. It's like everything just kind of fires on a bunch of stuff.
Hmm.
Um, and so the idea then is that we stop looking at individual neurons as like the unit of analysis. We kind of like move to a layer of neurons. It's like in these neural networks, usually things are processed in kind of like these layers. So you have like these like stacked layers on top of each other in a transformer network, for instance, or I think basically every major architecture for forever in deep learning kind of has these stacked layers to some extent. Um,
Yeah, yeah.
and so the idea is that if you look at a single layer, so a layer of neurons, it's kind of like maybe you have a layer it's like a list of like I don't know 1,000 or 10,000 neurons or something that form a layer, and you treat this like a high dimensional space, uh, and then the idea is that concepts are some linear direction in this space, uh, and the idea here is that the model is like actually using this as a form of compression. So each concept is not completely orthogonal. So imagine if you had like 10,000 neurons and forming some like kind of space, and you wanted to make every concept perfectly orthogonal as a linear direction. You can only have like 10,000 concepts because otherwise they'd overlap and you get interference. But
Hmm.
if you say like, oh, I don't care, that's fine. I'll just like let them overlap a bit. So the concepts are directions, but they're not completely orthogonal. Then this kind of means that you can fit like exponentially more concepts in this space. There's some theorem about this, but they overlap a bit and they kind of interfere with each other a little bit. But the idea is that the network's kind of okay with that. It's like as long as the interference is like not that much, then it's actually fine, and it can filter out some of the noise. So I guess like instead of like Spider-Man being like here and like organic chemistry being like perfectly orthogonal, maybe it's like a little bit non-orthogonal, and that means that like when Spider-Man's active, it's going to project a little bit onto the organic chemistry or whatever direction or French poetry
Hmm.
direction, and uh, vice versa. But maybe the network can just be like, all right, well, I'm just gonna like set a threshold and be like, anything below this amount, I'm going to kind of ignore as noise, and then if you just do this, you can hopefully still then compress like millions or billions or who even knows how many concepts into this space, and still kind of be able to do meaningful computation with them and filter out kind of noise. Um, and this is like, it's like pretty smart for the network to do this, but it's also very annoying for interpretability because this means that now each individual neuron you watch is going to fire on like lots of different things. Because you have theoretically like more concepts than there are than you have dimensions. This means that typical linear algebra tools don't work. So things like, like usually if you wanted to just find just the meaningful directions in some vector space, you'd use like principal component analysis or something.
Hmm.
You just kind of find them, but that can only give you as many kind of directions as there are, dimensions in your hidden space. And according to this theory, uh, we should expect that there's like dramatically more concepts than we have dimensions. And so we need some tool that can let us recover these directions even though they overlap with each other. And that's kind of where the idea of like sparse autoencoders come in.
So if you take the vector of activations at some particular layer, then it might be the case that if the first coordinate is zero point 0.1, if the second coordinate is minus zero point 0.3, etc., then if the vector is that, then the LLM is thinking about Spider-Man, or like will be more likely to predict Spider-Man. But it's not quite that. It's that any scalar multiple of that vector will mean the LLM is about to output Spider-Man or is thinking about Spider-Man. So this is you can't prove this. This is a hypothesis, right? Called the linear
Yes.
representation hypothesis. That if you do find some vector that represents a concept, then any scalar multiple of that vector will also correspond to that concept.
Yeah. Yeah, that's right. Yeah. So it's like maybe the magnitude of the vector is like how how much it's thinking about it or like how much it believes it or I don't know, something like this. I guess would be kind of the idea.
Hmm. Hmm.
Um and so I mean in practice this is obviously not completely true. Like you can't just keep going in infinitely in a direction. Like you'll definitely break the model if you just start uh you know put Spider-Man at like a billion and like add it into the activations of the model. Like things will kind of explode. Um but yeah, so I feel like also there's this idea of like linear concepts is like a people kind of means seems to mean different things to different people, but
Mm.
um, yeah, I think like generally this idea that like there's some kind of like direction that is used to represent a concept. Um, broadly magnitude means kind of either certainty about the concept or like strength of the concept within some like reasonable range. Uh, so things that would be invalid under this would be like this idea that like you have this direction and like from here to here is Spider-Man and then like from here to here is like organic chemistry. So like different parts of this band are like different things. So yeah, so that would be disallowed under this theory basically.
Right. And
Um,
it could have been like that, right? Like it could have been that we looked in LLMs and that was the way in which they calculate. So we kind of got extremely lucky that this linear representation hypothesis does have some truth to it.
yeah, yeah, I think that's right. Yeah, I mean, it very well could have been there's be some like even it's like super crazy nonlinear thing going on. I mean, like probably some like there probably is some of that to some extent. I guess like you can imagine there's probably not a lot because like for the model itself, it is useful if it can I mean, basically all internally look at like what's in a transformer. It's a lot of these like matrix multiplications and stuff. And so for the model itself, it's very useful if if it wants to like understand like is Spider-Man being talked about if it can just like do a single dot product with
Mm.
the residual stream or the activations, just be like yes or no. So kind of almost like internally for the model, it's like very useful. It doesn't have to do some kind of like galaxy brain computation internally to like figure out what's going on. If it just represents stuff as linear directions, then it's pretty easy for the model to also use those representations itself. Um,
Right.
I mean, there's also this idea of like like manifolds or like maybe in some high dimension, like maybe things are not fully linear. Maybe there's some like surfaces that are the actual important thing for some concepts. Which yeah, I mean, like I think it's like clearly true that there are going to be things like that in the model, but it also seems like there's a lot of evidence that at least for like most stuff, things are like basically linear, just within some degree. Because like things that work really well are like linear probes. So you can just like make a little linear probe for a concept. You can also just like take a concept direction and just like push it up or down and like make the model think more. Yeah, like I mean, so famously like Anthropic did this with the Golden Gate Bridge, where they made a version of Claude that was just like obsessed with the Golden Gate Bridge by basically like finding a direction that seems to correspond to the Golden Gate Bridge-ness and just like clamped it at some high value in the model. Um,
Mm.
and then this basically made Claude just like obsessed with the Golden Gate Bridge and like would try to talk about it constantly. It was kind of like make every conversation about the Golden Gate Bridge. Uh, and it's like you can even do like really, in my opinion, like seemingly stupid things that seem to seem to actually work pretty well, shockingly. Where it's like you say you have the model talk about like uh I don't know like things that are happy and you just collect some internal activations from the model and then you have another then you make the model talk about things that are sad and you like collect internal activations from the model and you just like subtract them from each other and get like a vector out of that and you're like, oh, this is the happy vector because it's like happy talking about happy things when it's talking about sad things. Then if you just like add that into the model again, it'll like make it happier. Like, things like this. Like, I mean, how this works is like insane to me that you can just do something like this simple and like kind of seemingly dumb. You're like, oh, it actually works. Like, clearly what's going on in the model can't be that galaxy brained if that works.
Or that alien.
Yeah. Yeah. I mean, it's also weird that like stuff like this works, and it's like, oh wow, interpretability must be easy then, because we can just do these simple, very dumb things like subtract whatever the neuron activations when it's happy minus the ones that it's sad, so just like and then just add that in all the time to make it happier like that. Like if that works, like surely this can't be that hard. But then it's
By make it happier, we mean make it output happy text.
yeah, yeah, exactly, yeah, yeah, or at least like make it behave as if it was happy. Yeah, so you can find these like vectors for all kinds of stuff like this. Yeah, so it's like the fact that this kind of stuff works kind of implies there's something sort of linear going on.
Mm.
Yeah, I mean, I guess if if people who've ever tried this, like it also kind of screws with the model a bit. Like you kind of break the model a little bit if you take this too far. If you're
Mm.
like be extra happy and he's like at some point the model just kind of like falls apart. And I mean, it is kind of like a very crude intervention. I feel like you're like hitting the model in the head with a hammer or something. It's just like
Yeah,
kind
yeah.
of it's definitely very unnatural for the model to just be in this state. But uh, yeah, I mean, the fact that it works at all is like kind of mind blowing to me.
So we got this idea of like directions in activation space represent concepts.
Hmm.
But as you mentioned before, like the model's going to be thinking about more than one thing, right? Like in order to correctly predict the next word, surely it doesn't just have to think about Spider-Man. It also has to think about like the grammar of the sentence, whether it
Yeah.
needs a verb or a noun, whether it's in the passive or active voice, and also like other content previously in the text. So it's probably going to be representing multiple different concepts at the same time. So the hypothesis then is that this activation vector is actually a sum of many different vectors pointing in different directions, representing different concepts, and they're added together to produce this representation that collects together all of those concepts together. Is that roughly
Yes.
correct?
Yeah. Yeah. Exactly. Yeah. So it's like the idea would be that like maybe the model can represent, say, like billions or who knows how many concepts in theory with these different directions. But any given activation, there's only maybe like some small number of those potential concepts that are actually there. It's like, so instead it's about like Spider-Man, like, it's probably representing Spider-Man and like superhero and noun and human and stuff. Uh,
Hmm.
but there's so many there's so many concepts that are like it's not thinking about at that time. So the hope is that even though there's like so many, potentially millions or billions of concepts that could be represented at any given time, there's like some small number, you would say like a sparse number of concepts that are being actually represented. So maybe there's like 100 or 200 or something. Um, Guess we don't actually know how many there are, but yeah, theoretically, it's like probably something along those lines of like maybe a few hundred concepts max
Hmm.
uh, per token that you're evaluating. And yeah, this would include things like the grammar, like the previous context of the sentence, and all this kind of stuff. Um, yeah, yeah, and so this turns out to be very important that there's a sparse number because you know if there wasn't, then we'd be a bit screwed to try to find these concepts.
Yeah, yeah. So the idea is to try and reverse engineer this to like for any given vector in activation space, try and split it up into its component concept vectors and how big each one is. Um, but if there were like uh so suppose you're in like 1,000 dimensional space. If each vector was made up of 1,000 concepts, then there'd just be no way to like, well, let's say 1,000,000 concepts, then there'd be no way to disentangle it. But because each vector, we make this as hypothesis, right? This assumption that each vector is an addition, a linear combination of just a small number of concept vectors, say 100, even though there's like a million or a billion uh, available. So then this is called dictionary learning, or is this called
Yeah.
dictionary learning?
Uh, yeah. To be honest, I'm actually not entirely sure what the exact definition of these terms is. There's like a bunch of terms that can kind of all refer to similar things or the same things. There's like this idea of like sparse coding or compressed sensing or like dictionary learning, where it's this idea of like using sparsity to kind of like recover these. kind of overlapping concepts. Yeah, it seems like a lot of different
Hmm.
fields have all kind of like are all using kind of similar tools basically for this similar sorts of problem. Um, so dictionary learning, the idea is that you have what's called a dictionary, which is a big list of all the kind of like directions that you think are relevant. So in this case, the concept, like your guess, the uh, concept directions, uh, or rather, I guess you'd say you're trying to learn this dictionary, which is the set of the kind of like true concepts that the model's using. Um,
Hmm.
and this, so for like say your model has like 1,000 dimensions and it's hidden space, maybe you make this dictionary have like 1 million concepts in it or something, or how, I don't know. I guess it kind of depends how much money you have to run GPUs to how big you make this. But typically you make the number of concepts in this dictionary much larger than the hidden dimension of the model. And then the idea is that there's kind of like a bunch of these techniques that will let you um, hopefully recover these kind of true, we'll quote true concept directions, and figure out what are the sparse combination of these concepts that are active at any given state inside the model. I guess like the most famous of these techniques is sparse autoencoders for interpretability, but you know, but theoretically, yeah, like dictionary learning encompasses like a more broad class of algorithms. Sparse autoencoders are kind of like a very kind of like a dumb, simple approximation to like these more powerful dictionary learning techniques, but in practice,
Hmm.
they seem to just be very hard to outperform. So I don't know, something weird's going on there, but uh, yeah. Anyway, so yeah, sparse autoencoders, you can think of it just like as a dictionary learning technique, trying to
Okay.
recover these feature directions. Yeah.
Okay, so dictionary learning is trying to come up with this list of like 1 million vectors that every activation vector is made up of a linear combination of a small number of these vectors,
Yes.
concept vectors. Okay, so let's dig into sparse autoencoders. So people probably know what an autoencoder is, where you have this bottleneck. But sparse autoencoder is the other way around, where it gets bigger in the middle. So can you explain what's
Yeah.
going on there?
Yeah. So it's a bit weird. So it's like, for normal autoencoder, um, typically you have like this input dimension, and then you go through some kind of like constrained thing, and then you go back to that same input dimension, and you try to like force those ends to like be the same. Like you basically have a
Hmm.
loss. It says like I want you to like reconstruct this input, but like but through going through this like kind of bottleneck. And sparse autoencoder is like the kind of the inside is actually much wider than the input. So like normally this would be trivial because you can just learn the identity matrix if you have a huge like if the bottleneck in the inside is like enormous. And so the way that this works is you put some kind of sparsity constraint on the inside. So you're saying like um I guess like the traditional way would be like you say like, okay, well I want this sum. It's like I want you to reconstruct these inputs, but I want the just like the absolute value, the sum of the absolute value of all the things in the middle must be as small as possible. And so you have like these two penalties of make this the activation is like small on the inside, but also like I want a good reconstruction on the outside. So like the more
Hmm.
common technique now is you basically just say like, you know, uh, I want you to reconstruct this input, but you're only allowed to use at max like 20 things, 20 of these vectors can be active total per input or something like this. So you just like arbitrarily constrain it to only have a max number of things that can be non-zero.
Yeah. So then the input to this sparse autoencoder is an activation from one layer of the neural network. So like
Yep.
you would feed loads of text, and at each token like collect the activations uh, in that layer, and then you feed those to the sparse autoencoder, and it has to try and reproduce them at the other end. But in the middle, it's very wide, but the bottleneck is not the fact that it's crushing into a smaller dimension. The bottleneck is that it's got to make sure only a small number of these hidden neurons are active.
Yes. Yes. Exactly.
Okay.
Exactly.
And then how
Um,
does this get us the dictionary vectors, the concept vectors?
yeah, it's very weird. This works to me. But uh, so yeah, so it's like normally in machine learning, like you have some kind of loss that's like you have a loss that does the thing you want. You know, like you can imagine like if you're trying to like make a neural network like predict what, you know, like other dogs and images, like you would just tell it like here's images with dogs, here's the images without dogs, and then you just like give it a loss when it the closer it gets to being right. Whereas with
Mm.
sparse autoencoders, it's kind of weird because we don't actually know what the right answer is. Like we don't actually know what the true dictionary vectors are. Like all we know is the input like activations. Yeah. So basically like uh yeah, to me this is very surprising that this works. So basically you're just saying like, all right, if we have this sparse autoencoder that like is able to reconstruct the inputs and only use a small number of features, then like as kind of a happy side effect, it will learn like the dictionary will then contain the true features. It's kind of the theory here. It's like very surprising that this works. Uh, but it, you know, it really does seem to like, so, under, well, under certain situations. So like, you know, if you set up like you know, for instance, like a toy setting where you have like some true features and they all fire independently, and you make sure that only, you know, some small number of them are firing on average per or at a time, and you train a sparse autoencoder on it, like it really will find the, like when you look at the dictionary of the sparse autoencoder or like the decoder of the sparse autoencoder, it will actually just like learn the true things. It's like it's kind of mind blowing.
How do
Um,
you tell it's the true things?
well, you just like I guess in the case where you set up your own like kind of toy model, you
Oh,
basically
okay.
you define what the true things are, and you say like, oh wow, it actually does just straight up learn it,
Okay.
which is pretty cool. Uh, but you know, this in reality, you don't have like, you know, everything fires independently of each other, and you don't have, you know, you also don't know exactly like how many features there are to begin with. So you don't know how wide to make your source autoencoder, and like maybe you can never make it wide enough for a real language model, you know, things like this.
Hmm.
So then the question becomes like, well, yeah, under what situations can we actually expect it to learn the true features, and when will it not? And like if it doesn't, then like what's it going to do instead? Like how messed up is it going to get? Uh,
Hmm. Can I jump in for a
but
second?
oh yes, sure.
So like the autoencoder just has one hidden layer, right? So it's like one matrix from activation vectors to hidden layer. That's called the encoder, and then another
Hmm.
matrix from hidden layer to back to reconstructed activations, and that's the decoder. And then the columns of this decoder matrix, they're what you interpret as your concept vectors, right? And
Yes.
then the top K. So if it's K, then you're saying like at most K elements of the dictionary of concept vectors are present in each activation vector.
Right. Yes.
Okay. And then the activations in the hidden layer, they are like the coefficients of that linear combination.
Yeah, yeah. So it's like if you look inside the source autoencoder, like at the in the middle layer, so like yeah. So imagine like you take a activation from the model, and you have like this perfectly trained sparse autoencoder, like you'd run it through, and then it's going to be like, oh, like say like these 20 uh features or concepts or whatever have some non-zero activation, and you'd be like, oh, like, you know, like, and maybe like in the case we were talking about like with Spider-Man, it's like these concepts are like Spider-Man and person and superhero and whatever. Um, and I guess like whatever number you would see for as the activation for each is kind of like how strong this concept is inside the model.
Mm.
Uh,
Hmm. So then
yeah,
how do you tell what that vector actually means, right? Like you could run loads of text input through the model through the sparse autoencoder, and for each token it says like, oh, these concepts are present, but like what are the concepts in human understandable
yeah,
terms?
yeah. So this is like one of these things where it's like why why interpretability is like really hard. Is that like we don't actually know what the like, we don't know for sure what the right answer is. So it's like, you know, you get these, you train a sparse autoencoder, and you end up with like this big dictionary of numbers, and you're like, well, what do these mean? Like, what are these concepts? Yeah. So imagine like you find like a million concept directions. You still don't know what those concepts are. Like you have to then try to interpret the concepts. Um,
Hmm.
and so typically the way you do this, I mean, well, you know, there's a couple ways to do it, but the the most common way is you just basically run a bunch of text through the model, and then you kind of just like watch for each feature in the sparse autoencoder, like what does it fire on and how strongly. and you kind of like make a dashboard where you're like, all right, for feature like 137 in the sparse autoencoder, it seems like it fires a lot when it mentions a Spider-Man, basically.
You just have to eyeball it.
Yeah, yeah, you kind of just you kind of vibe it out. You're like, yeah, it feels like this is it's a Spider-Man concept. And like, yeah, 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 I feel like currently vibing it out is kind of the state of the art. I mean, you can also there's also like auto interp where you basically have a language model vibe it out for you. That seems to also be because it's like there's so many concepts. Maybe there's like it's just not really feasible for a human to look at them all and like vibe them all out.
Do you take like a huge number of you have like a huge number of sentences that all make one the sparse encoder all say contain a specific concept, and then you feed all of these sentences to another LLM and you say what do these sentences have in common, and then it tries to figure out whether maybe they all say Spider-Man or something much more subtle.
Yeah, yeah, yeah. So I see you give it the sentences where the source autoencoder is firing, or this feature is firing, and and like tell it exactly what tokens it's firing on and how strongly, and then be like, what do you think it's doing? Uh,
Could you
basically,
ask the same model that you train the sparse autoencoder on?
you could, yeah. I mean, you could. I guess in practice, people usually try to use like a frontier LLM. But yeah, theoretically, you could use any model that is capable of interpreting this stuff. Um,
Hmm.
yeah, I don't know. I feel like I don't personally. I don't know how much faith I have in current auto interpretability labels that they're generated. Like sometimes they're good, but sometimes they're just like kind of out there. I mean, it's like a lot of the time it's also even just like for humans looking at the sparse autoencoder dashboards, it's like kind of hard to tell for most of the a large portion of the concepts like what this is doing. Is this actually it was just like hard to see the pattern.
Mm.
Uh, I think this is also a problem with interpretability is that it's like very easy to like because you don't actually know what the right answer is and you see something weird in a source autoencoder dashboard, you can be like, oh, well, this is just how the model works. It's like doing something galaxy brain that my poor human mind just can't understand. Or it could just be like your source autoencoder is like learned something stupid and it's right the source autoencoder is just wrong, which I think is
Right.
probably more likely what's happening. This source autoencoder is just like learned some weird messed up mix of things and it's not actually like learning exactly the true things that you hope it would.
And this is because the loss isn't like fed the ground truth, right? Like, so the sparse autoencoder just wants to reconstruct. And by chance, it finds some of the concepts that the model seems to genuinely be using. But sometimes it might find a way to reconstruct that doesn't actually involve any of the concepts that the model is using. And then when you look at that, you'll be like, what does this represent? It's like, it doesn't represent anything. It's just
Yeah,
it's just how the sparse autoencoder learned to reconstruct.
yeah, yeah, yeah. This is kind of the core issue is that like this, yeah, exactly. Sparse autoencoder just wants to reconstruct the input as sparsely as possible, and you're hoping that like that will result in it finding the true concepts. But like, I don't know. Gradient descent is like very smart in a way. Like it can find all kinds of like weird ways to get better reconstruction uh sparsely that are not actually that don't actually involve learning the true concepts. Like it can find basically it's able to abuse like correlations between features or like I've even seen in some source autoencoders where it'll like depending on how it's set up, like you can actually abuse the superposition noise. So like it kind of like find ways to use the fact that there's some slight overlap between features to like do something hacky that gets it a better score by kind of abusing this fact. And you're like, no, 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 stop that. Like just I want like please don't do that. But yeah, I guess like constructing an algorithm such that yeah, I guess the trick is like can you make it make a setup where uh the source autoencoder has to actually learn the true features, and that's the only way it can get the right answer, um, and not
Mm.
get the right answer or get like a better construction by doing something kind of. I mean, I guess this is also kind of maybe a broader problem in machine learning. This idea of like your system finding like messed up ways to do the thing you're telling it to that are not what you intended. It's
Yeah.
like also
Yeah.
common reinforcement learning. You're like, no, 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 I wanted to get a high score by like winning the game, not by like just driving in circles, like picking up like stars or whatever.
there's a few different variations on sparse autoencoders, and they're all aimed at like trying to figure out these concepts better, more accurately. But because there's no ground truth, it's hard to evaluate which of these methods is actually doing better and which are doing worse. So this is the motivation behind your work, right? Can you talk about the paper you've just submitted?
Yeah, yeah. So this is kind of something that's been like driving me crazy for a while. Is like you come up with some like Galaxy Brain new sparse autoencoder architecture, and it's like very hard to tell if it's actually working or not, or like how well it's working because um yeah, because we don't really know what the ground truth is. And language models, like, we have some like benchmarks that kind of like you know like the kind of like they're great, and we I very much love them, but they are also kind of noisy, and it's a bit hard to like tell if you're making progress a lot of the times or differentiate. Is this like LLM actually better than another one, or is it just kind of some noisy benchmark, or maybe the benchmarks themselves are kind of flawed, or
Hmm.
um, stuff like this. So, uh, yeah. So basically, my most recent work is trying to build like really elaborate synthetic data environments for sparse autoencoder training. So kind of basically saying like, okay, like forget language models for a second. We'll just like make make our own like synthetic concepts. Where basically like this thing we were talking about like earlier of we have these linear concepts, and they're all kind of superimposed, and they kind of have correlations between their firing patterns, and all the reasons that we think that it or basically like what we were saying like is our hypothesis of how concepts are represented in language models. Like let's just like make some concepts manually, just create some concept directions that overlap, give them kind of
Hmm.
arbitrary firing patterns and probabilities and magnitudes, and just see like can current source autoencoders actually learn those if we give them this test bed where we actually know what the right answer is. Um, and because the benefit here is like once you actually know what the ground truth is, like it just becomes so obvious like instantly when this first autoencoder is not working. Like you can't just do this hand wavy thing where it's like this first autoencoder does something very broken, and you're like, oh wow, the model it's brilliantly representing these things in some way that my small human mind can't understand. You're just like, no, wait, hold up, I know what the right answer is, and this is not the right answer. Like it's doing something stupid. Uh, and like yeah, so basically the idea is like let's make these synthetic data experiments like as realistic as possible. Like instead of just having like ten true features that all fire independently, which is kind of like this what people typically will do for these toy model experiments. Like do like okay, let's have like tens of thousands of features. Let's put like realistic firing probabilities and correlations between them. Like actually put superposition noise, so have them actually overlap with each other, and then try to train sparse autoencoders on these and see like does it actually learn it, and then yeah, hopefully, yeah. My hope is that if we use this as a test bed to iterate, we can get like much more fine-grained feedback on what's working and what's not working, and uh, then hopefully then transfer that to real language models. And well, I guess the hope is that I guess the hope is that this test bed is actually like realistic enough that when you train a sparse autoencoder on this and it works super well, that would also transfer to language models. But
Like, because in your test beds, you're like making the linear representation hypothesis true, right? And
yeah,
like you're forcing the fact that there are like some known number, or well, not known, but like some fixed number of dictionary vectors, and they're always represented sparsely, and there's no other vectors that it could be representing, etc. So it might be the case that like, yeah, you find some SAE architecture that works really well for your test bed, but if those assumptions don't hold fully in the organic LLM case, then that architecture might not actually work very well in real life.
yeah, yeah. So that is a risk. At least like so far, it seems like when in this kind of test bed we made, like we do see a lot of the failure modes that you see in real language model LLM or SAEs, where it's like things like so I guess in the arc of SAE hype, everyone got very excited in 2024, and then like Mark Andreessen, and then kind of in interpretability, people were like, like after 6 months, everyone stopped high fiving, and then it's kind of like, well, so have we solved it? Like, can we just prove? Can we do like really useful things with these? And kind of discovered that it's like actually sparse autoencoders seem like they're underperforming relative to like other interpretability techniques. Like just simple linear
Mm.
probes are like crushing sparse autoencoders at
Hmm.
everything. So there's like a paper that came out where basically showing like basically doing these like simple like probing benchmarks. Where you're kind of like saying, okay, well here's a bunch of like concepts that I know about, like you know is this a dog, or like is this a person, or whatever it is, and then kind of training and then taking your sparse autoencoder and being like, okay, well, does the sparse autoencoder actually learn features that seem to map onto like the concepts that I know are, well, at least I assume should be represented by the model, like someone
Hmm.
being, this being a dog or a cat or something. um and basically found that for these kind of supervised things, like linear probes are just outperforming SAEs like crazy. And so we actually see the same thing in these kind of synthetic benchmarks as well, where we see that SAEs are also not doing super well at like being or at being probes for the concepts that they should be ideally learning. Um, and like so that's kind of an encouraging sign, because that means like it gives us some more faith that like, okay, well, maybe we actually do solve it in this kind of limited case. Then hopefully that will actually transfer. So I guess like maybe as a broader theory, it's kind of saying like, okay, like even if the linear representation hypothesis was perfectly true, our SAEs would still be not performing perfectly, or not doing super great. And so therefore we should try to like, at least like, I feel like at the very least we should make SAEs work for like these kind of simple linear features and stuff. Like if our current
Yeah.
SAEs are not even handling that super well, then like we should have no faith that they're going to actually work on a real language model. Um,
Right. Right.
and like
But
if we get to the point,
these probing experiments show that the linear representation hypothesis at least has some truth. It gives you some confidence in it. And so it makes sense to then investigate, can we come up with an SAE architecture that does work well under the assumption of the linear representation hypothesis? And then
yeah,
another benefit of the work is like, if you do find an architecture that works really well under the linear representation hypothesis, yet doesn't transfer to organic LLMs, then that's a point of evidence against the linear representation hypothesis, or maybe means that it's only true in some limited sense for some limited set of concepts, but not in the whole space.
yeah, and I guess I'd also say like we should also like make these synthetic models better too. Like if we think that there's some other hypothesis as to what's going on, like we should build that into these synthetic model experiments. So it's like now
Mm.
we kind of have a model some kind of synthetic model that explicitly follows the assumptions of this whatever theory, and then like I
Mm.
use that as a test bed. Like, can we make some kind of, maybe it's not even SAE at that point, like whatever technique it is, like to recover these features, like can we at least, um, yeah, show that in this kind of synthetic setting. Uh,
Hmm.
yeah, but I think like also there's like, so the kind of the, supposed failure of SAEs, interpretability. I think a lot of people have also kind of used, I think there's like kind of a couple of things getting inflated here. People seem to think like, oh, well, I guess like linear features are false because SAEs aren't doing super well. And it's like, I'm also kind of showing here, it's like, no, like, even if the linear features are true, the SAEs would still not do well. So like you're not like disproving linearity. So like, I think there's like a lot of kind of,
Right.
um, I think people are like reading way too much into this, like assuming the SAEs are way better than they actually are currently. And I think this is causing a lot of like incorrect assumptions, like, oh, like interpretability is doomed. It's like, no, yes, okay. Sorry. I feel like I'm about to go on like a minor rant, but like, it's
I'm
like,
enjoying the run.
uh, so I feel like with interpretability, everyone kind of follows these like big hype cycles seemingly, where people get way overexcited about something and then get like then like way too down on it. Whereas, like I do think SAEs, like they are, it's okay. So like they're not perfect currently, but like it doesn't mean that the core idea behind them is inherently wrong or it can never be made better. It's just like, if if this linear representation hypothesis is true, or like at least close enough to true, and there is sparsity in the activations of the model, then like that means that this seems like it would be the right kind of thing to do to get at, to recover the true
Hmm.
features. I think it's pretty easy to show currently that like our current SEs are not up to the task. Exactly. I mean, like when I say that like, they're not up to the task, I mean like they still like get like mostly the right stuff. It's just like maybe it's like 70% right and like 30% like kind of nonsense in a mixed
Hmm.
into a latent. Um, but I think like this should just mean like, okay, well, let's like make them better. Like let's fix them. Like let's try to improve them. But, like I think things aren't like 100% like awesome and like solves everything, or terrible and useless. It's like, we do have the ability to like improve to these techniques and like actually make them good if they're not good. Uh,
Mm.
yeah. Anyway.
So what?
Um,
So you've got this test bed. of activations that obey the linear representation hypothesis. And then you experiment three different SAE architectures. So like vanilla SAEs, um, matching pursuit SAEs, and matryoshka SAEs. So what did you find when you ran these three different techniques on your testbed?
Yeah, yeah. Well, I guess we had a few others too, but yeah, I was talking about those for now. So there's a couple interesting things that are going on here. Like, I mean, so the standard L1 SAEs that everyone used to use initially, like they don't do super well. Like everyone kind of that's like not shocking to anyone because they kind of have a much known issues, which are why they're not in practice used anymore. Um,
Hmm.
so the other technique is top K or batch top K, which is kind of like the standard. Yeah, I'd say batch top K is like the most standard technique. That one also like it does better, but like also not still like still not perfect. Like it's still not getting like amazing F1 scores at these like detecting the correct features and like we also kind of check like are the features being learned exactly do they exactly match the kind of like underlying ground truth features and like they like 70% match. But that's still pretty far from
Hmm.
100% matching. Um, so there's also the other techniques that are interesting are matryoshka and matching pursuit. So Matryoshka is I think is like widely viewed as like this current state of the art in terms of like it's a kind of uses this like nested structure within the SAE itself. It's like a lot more complicated to actually set up and train and stuff, but and they also should have some like theoretical limitations too. But we do actually see that like in this synthetic testbed, Matryoshka SAEs also are the highest performing one. But there's like kind of this interesting dichotomy where they get the worst reconstruction. Uh, so they're actually the worst at reconstructing the input, but they're the
Right.
best at actually learning the true features. So this is also kind of like showing that like learning the true features and like reconstructing the input are not the same thing. So these other SAEs are way better. So for instance, matching pursuit's the opposite, where it's like insanely good at like, reconstructing the input. Matching pursuit is like basically more of a direct kind of powerful dictionary learning technique. It's one of the most old school dictionary learning techniques that exist. And it's like yeah, it crushes like reconstructing the input, but does it via not learning the actual underlying features. Basically, it's like really good at abusing these underlying kind of correlations and structure and the latents or the features of the model rather than actually just learning the directly matching the features.
Hmm. Hmm.
So yeah, I don't know. Yeah, basically like, these are things that we kind of see in LLM SAEs as well. So it's kind of nice that we're like, oh, that also occurs here too. That's also a good sign that maybe this kind of test bed model is actually a decent thing that you should test your architectures on. And if we could hopefully solve it or get SAEs that are able to get like perfect or near perfect scores on this, then maybe that would be a good sign that we've like uh, we're making real progress to improving these techniques. And because like
Right.
I do
So
think
the
like the
problem that you're the,
oh
the
sorry
the problems that the architectures have on the testbed are the same as the problems that the architectures have on real organic LLMs, and so this gives you a good hint that the testbed is a is a really good proxy that you can test things on, where you also have a ground truth.
yes exactly or at least like well, I mean I guess it's like hard to say that they're like exactly the same failure reasons. I mean we see like failing in similar ways, so that
Hmm.
hopefully that's like for the same reasons too. I guess it's also possible that like they're failing for some completely different reason on LLMs. But
There's a
I don't know.
conspiracy. Yeah.
I mean, I guess I kind of view this as like if you're making a car and like your car just drives down the street at like a slow speed and then just like starts bursting into flames, like that's probably bad. And you could be like, oh, but what about when you're on the highway? Like maybe it'll work then. It's like I don't know. Maybe if it can't handle going down the street at slow speeds, like maybe we shouldn't be driving on the highway to like see how it how it handles there. So I kind of view this like kind of test bed as more like let's try it on like a flat road with like no other cars on the road, and like if it still is bursting into flames, then you know let's make it not burst into flames there first before we then you know
Listing in the flames of this metaphor is Mark Andreessen getting overexcited and writing to Parliament.
yeah yeah yeah. I mean I don't know. Yeah, maybe after we solve all these problems in this test bed, maybe who knows? Maybe we'll actually get to the point that Mark Andreessen can right into Parliament and not be completely full of himself. But I think yeah, at the very least, like let's like solve it. Like let's handle like the simple test bed first.
Yeah, yeah. I think this happens a lot in machine learning, right? You want some toy case where things aren't perhaps aren't exactly representative, but it allows you better feedback signals and a maybe a tighter feedback loop. And so you can progress more quickly, and then you just hope that it generalizes to the organic case.
Yeah, yeah, exactly, exactly. Yeah, and so I don't know. Just trying to do the same thing for SAEs. That's the goal of this work. Yeah, so this is also kind of something that building into the SAE Lens library, which is this open source library I work on as well. With the goal of trying to make this like these kind of synthetic models like super easy for people to use and train on and iterate on. Um,
Mm.
yeah, also if people have ideas they want to contribute back, please do open pull requests at SAE Lens. And
So
yeah.
SAE Lens allows you to like more easily train sparse autoencoders specifically on your synthetic dataset or in general.
Oh, just in general. I mean, so SAE Lens is like it's a library for training and loading sparse autoencoders. So it's kind of yeah, I think it is probably the most commonly used sparse autoencoder library at this
Hmm.
point. But yeah, I mean, it's got I don't know. I mean, at least it has the most stars on GitHub, if that's a reasonable proxy. Uh, but I mean, to be honest, like most people using it are probably using it for loading SAEs rather than training, just because I think a lot of people find training SAEs a bit scary, but they shouldn't because it's not actually that scary. But um, yeah, so SAE Lens, like one of the things it'll let you do is for when people like train their own SAEs and upload them to Hugging Face, like we try to make it very easy to load those in SAE Lens. So in the same way, I guess you can kind of view it like Hugging Face, where it's like someone makes a language model, and then if you want to actually use it, you'd load it from Hugging Face, like in the same way that in
Hmm.
that kind of same vein, like when people train SAEs on open source models, we try to collaborate or collate all those into SAE Lens, and make sure that we can load them and convert them into the SAE Lens format, and like just make it dead easy to load and run in a Sparse Autoencoder. Um, yeah, we also support training and training on language models, and yeah, now trying to add a lot of this synthetic data stuff in as well. So make it really easy to train on synthetic data, do little synthetic data experiments, or large scale synthetic data experiments too. Um, yeah, that's
Cool.
the next frontier.
Maybe I should trade a sparse autoencoder.
Yeah, you should.
So you did this work as part of the MATS AI safety research program. I've heard this program can be a bit intense. So can you tell us what it's like to do MATS and how you got interested in AI safety in the first place?
Yeah. Yeah, Mats is great. Nothing but positive things to say about Mats. Highly recommend everyone do it if you can, or if you're interested in space. Um, yeah, so the way Mats works, I mean, it's kind of like almost like a mini PhD or something. It feels like where there's all these kind of supervisors that work on different things, and you kind of like apply to a supervisor to work with them on a project. Or, I mean, I guess like your experience is also probably going to be very colored by the supervisor you have. So in the same way that your PhD would also be very different depending on the supervisor. Like some people are more intense, some are more laid back, some are more like
Hmm.
some of them will give you a project, some of them will kind of want you to do your own, come up with your own project. Um, but yeah, it's a program. It takes place in Berkeley, in California, for 3 months, and then there's an extension in London, which is a bit more kind of free form. And yeah, I think it's great. Highly recommend it. Nothing negative to say about it really. It's just awesome. Uh,
You have freedom to
th-
pick your research project.
yeah, it just depends on your supervisor. So yeah, in my case, my supervisor was Adria Garrigo Alonso, and he's been great. Yeah, he's basically given me a lot of freedom to kind of pitch what I want to work on and kind of support me in that. And I think that's been very helpful. Um, yeah, so I think it's a good program. As far as AI safety, so I got into this. Uh, well, London just happens to be a very good place for AI safety. Kind of interestingly, because there's this like hub in London called LISA, which is like London AI's safety wait, no, London Institute for Safe AI, something, I think it was something like this.
Yeah,
Anyway,
that,
there's like a lot of organizations in London. There's a lot of good programs. I did like this laser program, which is takes place in London at LISA. It's another great program. Uh, and I don't know. Yeah, I guess I kind of got into safety via kind of the interpretability stuff, where I was trying to understand kind of, well, yeah. I mean, my PhD kind of like took some turns. Initially, I was trying to do some like neurosymbolic stuff, and kind of decided that wasn't really going anywhere, and then tried to understand. It was like, oh, maybe if I can understand how the models are representing knowledge, then you know, maybe that's like what we need for neurosymbolic stuff. And some of that I ended up getting into interpretability via that angle. Uh,
mhm.
and yeah, I just kind of found Lisa and Laser Labs and all these programs in London that are really great. Um, so yeah, London I think is a great place for any kind of AI safety stuff as well. It's also the I guess the UK and London has the UK AI. Well, I guess it's AI Security Institute now, since AI Safety Institute, but they rebranded. But yeah, they also do a lot of great work, safety related stuff. They do interpretability as well as other stuff as well. So there's a lot going on in London. Um,
Mm. Hmm. And
yeah.
you also work at the same time as doing this research on your PhD. You also work part time for Neuronpedia. So
Yes.
what do they do, and what do you do with them?
Yeah. So Neuronpedia is a uh, it's like a hosted. So initially they started off doing like hosted sparse autoencoder dashboards, and so you can look at, say, just kind of explore, for whatever language model you're interested in. Look at some dashboards that Sparse Autoencoder is trained in that language model, and kind of play with steering the language model. So taking for instance, you can make your own like Golden Gate Claude basically on Neuronpedia if you wanted to. They also
Hmm.
host a lot of interactive research demos from some of the big labs, or just kind of interesting research groups. So there's some pretty cool collaborations with like Anthropic and DeepMind. Um, like so, for instance, like Anthropic has this new like circuit tracing stuff, which is kind of like an extension of Sparse Autoencoders, but dramatically scaled up to try to like figure out exactly like trace the entire flow of concepts and knowledge through a model's forward activations. So there's like demos of this on Neuronpedia. There's some new work with, I think it's like persona vectors, trying to like keep the model from going off the rails using, again, some kind of steering technique, not so much autoencode related, but uh, like just kind of linear steering like we were talking about before. Yeah, they're a great org. So SAE Lens is also part of so the parent org of Neuronpedia is Decode Research, and so SAE Lens is officially part of Decode Research. So like I said, mainly been working with Neuronpedia via SAE Lens, because SAE Lens also powers a lot of the tools on Neuronpedia as well for SAE visualization. Um, yeah, Neuronpedia is awesome. Check it out. Pretty good platform for kind of just playing around with sparse autoencoders or getting a feel for steering or any of this stuff. Um, yeah, highly recommend it.
It has some nice visualizations, if I remember correctly.
Yeah. So the main guy who does it, like Johnny Lin, is just like kind of a genius at front end uh, design and stuff. I feel like, yeah, which is very, I don't know, it's really very rare in the research world to just see like very beautiful, interactive, visualizations and demos and tools and stuff like this. So I think it's really valuable. I think it does a great job with it as well.
Hmm. Nice. Well, I've really enjoyed chatting with you about your work. Really hopeful that this test bed produces more research into good SAE architectures, and the AI safety community doesn't give up on it so easily. Um,
Exactly.
that something nice comes out of it. So yeah, good luck with the review process, and thanks for coming on.
Oh, thank you. Yeah, great talking with you, Ruben.